All right, you guys. So continuing from that worked out example, this is again that same program with your post-recursive count and your pre-recursive count. So again, when you had 10 and 12 with a post-recursive count where the recursive call was at the end of that method and there was nothing after it, what would you have seen? 10, 11, and 12. And in count 2, when your count 2 goes on before the print, then it's going to hit that base case, only after which it'll move on to printing. So therefore, the first thing that'll be printed would be 12, and then 11, and then 10. And hence, this is what your output would look like. Okay, so this kind of a process would actually remind you of something called a stack, especially what we saw in our second example with count 2, that makes that stack even more prevalent. So let's see, what does that mean? So Java has a special internal data structure called a stack that is hidden from the programmer. A stack is a data structure that will only access data from one end, usually the top, in such a manner that it behaves like a LIFO, which stands for data is accessed last in, first out. Program's execution sequence is handled by something called an index pointer. The index pointer, or IP for short, contains the next memory address of the line to be executed. So it says an IP which points to a memory address is a computer, as in no way related to the Internet IP protocol, in case you were wondering. Okay, so basically, let this example show you that same count 2 that we saw. Now, what did they do? They put some additional print statements before and after it to give you a better understanding of what happens, like how is it really behaving like a stack. In common terms they use for stacks is pushing something on a stack, so that's one thing over the other, and popping things out of the stack. So whatever is last in would be first popped out, and so on until it hits the end of the stack. Okay, so again, this is the same count 2 example that we worked out. So you're passing in now two different values. There we passed it 10 and 12. So this is 100 and 105. So let's see, if 100 is less than or equal to 105, it says interrupt method completion pushing a on stack. So this is going to push the 100 on a stack first. Then what's going to happen? It's going to call count 2 again. Now it's going to call it with 101, 105. It's not going to move on to these two print statements. It's going to go ahead and solve for 101, 105. So therefore, it's what all is going to push on the stack. It's going to push 100, then 101, then 102, then 103, then 104. And then at 105 is less than or equal to 105, it's also going to push 105. And then it's going to call count 2 as 106, 105. And right there at 106, less than or equal to 105, it's going to be false, right? So therefore, right at 105 plus 1, comma b, it doesn't enter the if statement, so you can count it complete. Therefore, now it would start popping things from the stack. So now if you see, it would be popping a, and what would a be now? 105, displaying popped value 105. And then it would complete the previous one, which was partially over, right? So it'll pop 104, and then 104. Was the popped value. So therefore your output would look something like this. So it pushed until 105 and then it popped the 105 and displayed the popped value. Okay, you guys will get used to it. If this is causing confusion, you will understand the pattern more when you see more examples. All right, so let's say fundamental recursion concepts that all recursive methods require an exit or a base case that stops the recursive process. This is nothing new. We've heard about that already. In order to make a purposeful recursive program, you have to have a base case. So it says the stack controls recursion since it controls the execution sequence of methods and stores local information. This is important, you guys. It says every method call requires the completion of the call method even if the execution sequence is interrupted by another recursive method call. So even though you went and you solved that 105 case, right after that, it has to go ahead and complete the 104 case, and then the 103 case, and then the 102 case, and the 101, and then the 100. Incomplete recursive calls result in a last in first out execution sequence. Okay, let's see. Now these examples are going to show you how recursion can be turned into a useful program. Now, say if you were trying to solve a program where you were trying to add the numbers all the way from 1 up to the parameter you pass it. So say example, your goal was if you called sum1 and you passed in a number 6, you wanted it to compute the sum of all the numbers from 1 up through 6. Likewise, if you called sum2 and you passed in a number 100, you wanted to find the sum of all the numbers from 1 through 100. The only difference between sum1 and sum2 is they both have the same goal. Sum1 is solving it using the iterative fashion where you have a for loop. Sum2 though is solving it using a recursive fashion. So briefly looking at the iterative, right? It seems simple enough. You're making a sum variable, initializing it with 0, and you have a for loop starting from 1 less than or equal to whatever parameter you pass it, so in this case 6, and then what are you doing? You're adding 1 to sum, which was 0, then you're incrementing k, so you're adding 2 to that previous value of sum, and then 3, so therefore ultimately you'll get the sum of all the numbers from 1 through 6. Okay, what about sum 2? In sum 2, how is it behaving now? You're passing in a parameter, it's checking if that parameter is equal to 0. If it's equal to 0, it returns a fixed value, which is 0. If it's not equal to 0, which in this case it's 100, right? So it's going to return 100 plus sum 2 of 99. So then it's going to go ahead and solve for what is sum 2 of 99. So maybe looking at 100 and trying to trace the path would be a little difficult. So let's pick a smaller value. Let's pick sum 2 of 4. Okay, so if I was trying to find sum 2 of 4, which means 1 plus 2 plus 3 plus 4, let's see whether it really does that. So if 4 is equal to 0, which it is not, so it'll do the else, and it'll return 4 plus sum 2 of 3. Okay, then it's going to go ahead and solve sum 2 of 3. So it'll look something like this. So you have the first call with n equals to 4, and it goes to 4 plus sum 2 of 3. Now, in order to solve this, it needs to go ahead and make its second call of 3. It'll be 3 plus sum 2 of 2. Now, in order to solve this, it needs to do this. The third call, 3. This is the third call when n is 2. So you have 2 plus sum 2 of 1. And then your fourth call, sum 2 of 1. So it'll be 1 plus sum 2 of 0. And right here, when it does sum 2 of 0, remember where you had that if statement? If 0 is equal to 0, return 0. This is where it actually gets its fixed value. It'll stop calling sum 2. So basically, sum 2 of 0 evaluates to 0, and then you can feed in the values. So then sum 2 of 1 evaluates to 1 plus 0, right? Sum 2 of 2 evaluates to 2 plus 1 plus 0. Sum 2 of 3 evaluates to 3 plus 2 plus 1 plus 0. So therefore, what would sum 2 of 4 evaluate to? 4 plus 3 plus 2 plus 1 plus 0. And there's your answer, 10. Okay, so this way of creating this table, you guys, I highly encourage that you take this approach to solve it. It'll really help you understand those different layers of this problem, of these kinds of problems. This is another way to look at the same example, but now it's starting from the base case to start. Okay, so it's starting from the base case. So you have the base case is sum of 0, right, which is 0. Then it evaluates sum of 1, which is 1 plus sum of 0. And then sum of 2, which is 2 plus sum of 1. Then 3. This was finding sum of 5. The previous one was sum of 4. So therefore, this will end at 15. The other one ended at 10. Okay, so this is just another way. Some people prefer this, some people prefer this. But just realize what is that base case. Okay, so now this is another example, but this is looking at factorial. Okay, so you guys have probably seen or heard of the word factorial before. Basically, if somebody asked you to find 5 factorial, what they're asking you to solve for is what is 5 times 4 times 3 times 2 times 1. Okay, now again, when you see a pattern like this, again, you could use your regular looping structure, which is the iterative structure of doing it, where you start from, say this is fact 1 is the iterative and fact 2 is the recursive. they both again have the same goal. So fact 1 with 6, what is going to happen? It starts at 6. 6 is greater than 0. You're taking temp, which initially has the value of 1, and you're multiplying that with 6. And then you do k minus minus. So then whatever is stored in temp, which is now 6, is going to be multiplied with 5. And then with 4, and then 3 and 2. And then once it hits 0 is greater than or equal to 0 is false, it will not enter the for loop. How about fact 2? Well, if you notice the way it's written, you're basically seeing again at that base case, right? That is when n is 0, it returns 1. And then else return n times fact 2 of n minus 1. So therefore, and they say that doesn't this look like the mathematical definition of factorial? So sometimes a recursive solution is a little more easier to read than an iterative solution, just because it looks more like the formula that you guys have been used to using. So just again, tracing it, this is doing it by the second approach from the base case to the start. So the base case is fact of 0, which is 1. Fact of 1, which is 1 times fact of 0, which evaluates to at 1. Fact of 2 is 2 times fact of 1, so it'll be 2 times fact of 1 is 1. So 2. So this is like functions, right? Then 3 times fact of 2. Fact of 2 evaluates to 2. So it's like 3 times 2 is 6 and so on. So fact of 6 is 720. This is the last example that you will look at, you guys. This is an iterative. This is again, so we looked at factorial. You looked at sum of numbers. Now this is greatest common factor. So greatest common factor in this particular example, and I believe you saw this in one other place. I can't exactly remember which other unit, but we did see a GCF, this exact function before, where you pass in two values, you make two variables, temp and rem, where rem is holding the remainder of 1 with the other. If the remainder is equal to 0, then you assume that one of those numbers, right, was the greatest common factor. Else, you assign the remainder and now you check the remainder again of that and that previous remainder, ultimately until it hits 0. And once it hits 0, then you have found your greatest common factor. Now again, this looks a little complex, but if you look at a recursive solution to this, it's a little more simpler to read. It's basically only this much. You have two values. You have n1 and n2. You are going to take n1 and check its remainder with n2. If it's equal to 0, you stop it right there. If it's not equal to 0, you're calling the same GCF2 again. You're passing it n2 and the remainder of that. And this until goes again. So if you had 360 and 200, the remainder was 160. So therefore, this did not happen, right? It then called GCF2 with 200 and 160. So then it went to solve this case. The remainder was 40. It solved this case. And then here the remainder is 0. So this is where, excuse me, this is where it ended. Okay. You guys, with that, this was all I was going to stop at for your very first lecture of recursion. You should have watched 3 videos by now. The part 1, the one that I showed you on the demo with the working on that slideshow. And finally, this is the part 3. With that, what I'm going to have you guys do is I'm going to have you guys work on a worksheet that is published there. I want you to be able to show me the working to all these different examples on the space provided on that worksheet. So just like how we made those tables indicating the call number, the value of n or a and b, and what that result would look like. So there were 2 approaches. One was starting from the base case. The other one was not starting from the base case. It was starting from the parameter value that was passed. So pick one or the other, but you need to show your working for each of these questions. And then I need you to submit that worksheet by today. Okay, so again, as you complete the worksheet, the other thing that I'm providing is you can actually just enter your final answers on the quiz. So there will be 2 things. There'll be a worksheet and a quiz just to see if your answers are correct. Okay. So with that, please go ahead and now complete the worksheet and the quiz. Bye.